Welcome back, chemistry students. This is Miss Ruark. We're going to do podcast 3.5, where we're going to talk about the structure of the atoms, or not the structure of the atoms, excuse me, the structure of the molecules and the compounds. All right, so molecular compounds. Remember, a molecule is a group of atoms that are joined together by sharing electrons or sharing bonds. Right? Oh, I know what I meant to put here. Covalent bonds. Sorry. Bicovalent bonds. Sorry. And a covalent bond is where you share the electrons between two or more nonmetals. Okay, just a quick review. All right. Molecular formula, such as C6H12O6, represents how many atoms of each element there are in the compound. And you can't find it by using the crisscross method, right? We can't take ions and cross them down to find the molecular formula, and the reason for that is because a molecular formula does not have ions. It's not ionic, right? Ions. All right, we can determine it by creating a structural formula. We call it a Lewis dot or Lewis structure. When we do this Lewis structure, we have to obey the octet rule, which means that atoms are all trying to share electrons to maintain or to achieve 8 valence electrons, and that would be the electron configuration for a noble gas. And the only exceptions to those would be hydrogen and helium, which both want not 8 valence electrons, but 2 valence electrons because they can't hold more than 2. Okay, Lewis structures. Lewis structures show the arrangement of the covalently bonded atoms. They use dashes to show the bond, the shared electrons, the bond, and they use dots to show the unpaired or unshared electrons, or the non-bonded electrons. All right, so for hydrogen, the hydrogen has 1 valence electron. How do we know? Because it's in group 1. So if we were to draw the Lewis dot structure for it, it would be H with a dot. Well, hydrogen is one of these things called a diatomic molecule, which means that hydrogen is extremely reactive and it cannot be found just as a single atom of hydrogen in nature. It has to be 2 hydrogens together, or hydrogen will be bonded to something else. Okay, so if it's diatomic, there would be 2 of them. So hydrogen can't be alone. Hydrogen would have to have, let's say, another hydrogen nearby. These 2 hydrogens say, hey, let's share those electrons. And if we share those, you have 2 and I have 2, so we're both happy. But we wouldn't draw it like that. We would draw it as H with a dash and then another H. And that dash right there shows us that there are 2 electrons that are being shared in that bond. Okay, when we draw Lewis structures, there's some steps you need to follow. First, you need to take an inventory of all your valence electrons. So you need to count up the total number of valence electrons for your compound. Then you're going to arrange the atoms. This is what we call the skeletal structure. You're going to draw your skeletal structure, and when you do that, there's a couple rules you need to follow. Okay, first, hydrogen is never going to be put in the middle, ever. Okay, some other ones that don't go in the middle are the halogens. Okay, halogens, group 17. They don't go in the middle, ever. They're always on the outside. Atoms in the middle are generally those with the greater electronegativity, and carbon loves to be the center of attention, so carbon's always going to be in the middle. All right, when you're drawing your structures, you want to make sure that they stay as compact and symmetrical as possible. All right, so then after you draw your skeletal structure, make sure that you subtract the electrons that you've used from your or your electron inventory, and then you're going to fill in your electrons starting around the central atom first until all valence electrons are used. If they're sharing electrons, you draw a line or a dash, and if they are not shared, you leave them as dots. So, for example, methane. Methane is CH4. Well, to do the total number of valence electrons, to do our inventory, we have 1 carbon atom, and each carbon has 4 valence electrons. We also have 4 hydrogen atoms, and each one has 1 valence electron. So that gives us a total of 8 valence electrons to play with. All right, well, which one's going to go in the middle? Carbon goes in the middle. So we put carbon in the middle, and we put hydrogens all around. Now, Ms. Ruark, why are you doing them top, bottom, left, right? Great question. Lewis structures are 2-dimensional structures, which means that you use your x and your y axis only. 2-dimensional structures. For 3-dimensional, we get into the geometry, and we'll get into that in a little bit. So make sure that you do 2-dimensional, top, bottom, left, right. East, south, north, west, however you want to think of it. All right, we've drawn our skeletal structure. How many electrons did we use to draw this? Well, each line represents 2, so we've used 2, 4, 6, 8 electrons. And we subtract that from our inventory, and we're left with 0. Now that's a good thing because we want to use all the electrons that we have in our inventory, but we got to make sure everybody's happy. Now, hydrogen wants 2, carbon wants 8. So hydrogen has 2 here, hydrogen has 2, hydrogen has 2, hydrogen has 2. They're all happy. Carbon here in the middle has 2, 4, 6, 8. So everybody's happy. Yay! All right. Try these. So here's some for us to try real quick. Hydrogen, there's 2 of them, and each hydrogen has 1 valence electron. And then there's 1 oxygen, and each oxygen has 6. That gives us a grand total of 8 valence electrons to play with. We've got oxygen and 2 hydrogens, so we'll put oxygen in the middle, and then 2 hydrogens. Now, why did I draw them like this? Because we want to keep them symmetrical. Remember, symmetrical. Okay. I've used 4 electrons. Each line represents 2 electrons. So I've used a total of 4, and I've got 4 left to go. Hydrogen here has 2, so it's happy. It's happy. Hydrogen here has 2, so it's happy. Oxygen only has 4, so it's kind of sad. All right, but guess what? It wants 4 more to make 8, and we have 4 more. So we're going to draw 2 up top and 2 on the bottom, and that frown gets turned upside down and everybody's happy. All right, so now I want you to try number 2 and number 3, and when you come to class, we'll go through them together. Do the same steps. Okay, multiple bonds. There can be more than one shared pair of electrons between 2 atoms. If you have a single bond, that means 2 atoms are held together by sharing 2 electrons, which would be 1 pair. A double bond is 2 atoms being held together by sharing 4 electrons, which would be 2 pair. And then, of course, if there's a triple bond, there would be 6 electrons being shared for a total of 3 pairs. Double bonds and triple bonds will never be formed with the hydrogen and the halogens because they only want 1 bond. Okay, so for example, if we had hydrogen, let's say hydrogen gas, we've already done this. We have the hydrogen with the other hydrogen, 1 bond. There's a single. All right, well, what if we had a double bond? Let's say we had CO2. So we have 1 carbon, and each carbon has 4 valence electrons, 2 oxygens, and each oxygen has 6 valence electrons. 12 plus 4 is 16. Okay, so we've got a total of 16 valence electrons to play with. Carbon always goes in the middle, so carbon goes in the middle with oxygens on the outside. And we've used 2, 4 electrons. So we subtract 4, and we're left with 12. All right, oxygen only has 2, so it needs 6 more to make it happy. Carbon has 4, it needs 4 more to make it happy. And oxygen has 2, so it needs 6 more to make it happy. We need a total of 16, but we don't have 16. We only have 12. When you have more, when you need more than you have, they have to share. So you draw in another bond. It doesn't matter where it goes as long as it's not between an element in hydrogen and an element in halogen. Okay. All right, subtract those 2, which leaves us with 10. This one now needs 4 to be happy. This one needs 2 to be happy, and this one still needs 6 for a grand total of 12, and we don't have 12. So we got to share. Now, it doesn't matter if you draw it over here, but we want some symmetry, right? So we're going to put it here. We subtract those 2, which gives us 8. All right, oxygen needs 4. Carbon's happy, and oxygen needs 4 for a grand total of 8. We have 8, so we're going to draw our electrons. And we're done. All right, and then if you had a triple bond, that would be like nitrogen. I'm just going to draw it for time's sake, but we will practice them in class. Okay, and a triple bond would show that there are 3 sets of electrons that are being shared. Okay, I earlier mentioned something about hydrogen being diatomic. Now, a diatomic molecule is a pair of atoms in element form. They're not compounds. They are just diatomic molecules. They don't exist as individual atoms in nature because they are too reactive. All right, so which ones are they? They are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. There are only 7 of them. Okay, so you do need to remember these. Remember. Put them to memory. Because if you don't, you're going to have very many struggles as we continue to go on. All right, 3 ways to remember them. You can do Dr. Brinkelhoff, because look, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Spells it out, Dr. Brinkelhoff. That's the one that I use the most, but it doesn't matter which one you use. You can also do Heck, No, and the halogens. Heck would be hydrogen, and No is going to be nitrogen and oxygen, and then the halogens would be chlorine, fluorine, bromine, and iodine. Okay, so Heck, No, and the halogens. And you can also say the 7 diatomic, because if you look at them on the periodic table, they actually make a 7. Okay, remember those. All right, so octet rule is that rule that governs how to do Lewis structures, and it's something that they all follow, except, there's always exceptions, right? Okay, boron does not like 8 total valence electrons. Boron likes to have 6. So boron wants 3 bonds. 3 bonds for a total of 6 electrons. Okay, and then other ones, and we'll do examples of these in class, so you don't have to worry about drawing them out. But then the other ones are some of the atoms in the 3p block that have access to the d orbitals, and they can make more than 8. And I think that's multivalent, but I can't remember the word that I wanted to put there, so I guess it doesn't really matter. They just can have more than 8 electrons. So examples of those would be PCl5, PCl3, and SF6. Okay, and I would draw them out, but we can do those in class. You can try them on your own if you want. Okay, moving on. Lewis structures of polyatomic ions. All right, so here, all you're going to do, I want you to try this one. Just try it. Do it in pencil. It's okay. And when you come to class, we're actually going to do this one and some other ones. But when you do this, if there's a positive there, that means that you have 1 less electron. So you would have 5 electrons for your 1 nitrogen. So 1 nitrogen, there's 5. And then you have 4 hydrogens, and each hydrogen has 1 valence electron. That would be a total of 9 electrons. But guess what? Because that right there says that there's a positive charge on it, you have to subtract an electron for a total of 8 valence electrons. Okay? And then when you do your structure, you would have to put your structure in brackets. So you have your nitrogen and your hydrogens. And I just told you to try it, but I did it for you anyways, and that's what it would look like. So we're going to do a lot of these in class. Don't worry if you're not there with it. Okay, the last thing I want to talk about is molecular geometry. This is where we talk about that third dimension of space. Okay, you have your x and your y axis. The third dimension of space is that z axis that we typically draw like this. The z axis comes out towards you and goes into the TV or whatever you're watching this on phone. All right, the three-dimensional objects are ruled by this thing called VSEPR, which is the valence shell electron pair repulsion theory. And all it says is that the negative charges of the electrons are going to repel each other and move each other as far away as possible, which creates that depth because now it's moving into the third dimension. So the common shapes that you could have for this. Let me change my color so you can see where I'm going. We'll do red. All right, the tetrahedral looks something like that. The trigonal pyramidal looks something like that. The bent looks like that. The linear is, well, it's linear. And then the last one we have is the trigonal planar. Okay. And I just want to show you the things now. When we get into class, we'll start playing with the model kits or maybe even balloons, but you'll be able to see the different shapes and you'll be able to identify them. Okay, I think that's it, ladies and gentlemen, so I will see you in class.